Thank you, Chip, for the kind introduction, and thank you to the audience. There's a much better audience than I expected on Wednesday night at the beginning of the conference. This is fabulous. And as General Clark said, this is a little bit preaching to the choir, but hopefully I'll say a couple of things that are you haven't heard before, and actually have a couple of graphs that repeat what General Clark said. So where's the click? I don't know how to. Is it this one?
Yes.
Nope, that turned it off.
It's the green button.
Now how do I turn it back on? Okay. There we go. So just quickly, as Chip said, I come from Arizona State University. Very proud to be coming from Arizona State. I've been there about 7.5 years. I come out of industry, the auto industry, so you might see a little bit of bias from that, and also the national security from a Department of Energy National Security Laboratory. But the Arizona State University charter, I think, is phenomenal, so I like to always start with it. Arizona State is a comprehensive public research university. It is the largest in the U.S. And what I love about what our president says, it's measured not by who it excludes, but whom it includes. And as we heard from the earlier talk, education is going to be incredibly important, and we need everybody educated, and an educated public would go a long way to solving this problem. But not just who we include, but then how they succeed. And by doing it through research and discovery of public value, which is why we're so focused on this particular problem that we all here are about. We take very seriously our fundamental responsibility for the economic, social, cultural, and well-being of the communities that we serve. So we're out to transform society, use use-inspired research, and engage globally. So not just the U.S. So ASU Lightworks, I, with Gary Dirks, co-direct the Lightworks initiative. And under Lightworks, we pulled together light-inspired research under one strategic framework. We envision a resilient and equitable energy future that's supported by innovations. Even though I'm a scientist and engineer, actually it's not always the most important. So innovations in technology, policy, law, governance, and of course markets. Pursuing breakthroughs to achieve energy security, but very especially energy justice, and to inspire future generations. We're very focused on the energy transition. We've heard we have the means to do it. We often look at the end state, but we don't often think long and hard enough on how we get from here to there. And I think it's very important, and what's the most likely end state and that we can achieve also depends on the pathway. And that isn't thought about quite enough, I think. We like to collaborate with like-spirited people, and I say that like-spirited, not like-minded, because diversity of thought is so incredibly important. And I think this room is almost certainly like-spirited, so and has a common vision for sure. So we focus, light-inspired is essentially solar energy. It's not exclusively solar energy. And what we love about solar energy is it's highly scalable and it's democratic. What we mean by that is it's distributed much more equitably than any other natural resource on Earth, especially when you compare it to oil, natural gas, and some of the critical elements that are going to be so important to the energy transition. So just to pull on that thread just a little bit more before I get to hydrogen and carbon, just ask the question, what can we do if we have 1% of land? A recent report came out with how we use land, and I just want to point and I don't think most people realize this, the built environment is only 1% of ice-free land. Humanity does use the majority of Earth's surface, but not for the built environment. It's mostly for agriculture and grazing. So 1% of global ice-free land, if we only had 10% efficiency solar to end use, and we hope to do better than that, that would yield 26 terawatts, and that's at end use. Primary energy today is 18 terawatts. At end use, that's about 7 terawatts. So that's 1% of land. Solar is enough of a resource. But, so sufficiently scalable for our primary energy needs. But that's not all our needs. Okay. So let's just take a step back for a minute and talk a little bit about trends. Some of this has been mentioned. Emerging economies, global economies, the world is developing. That means we're going to use more resources. We're going to use more energy, not less energy. But we also have, there is unfortunately increasing income disparity. We'd like to solve that. But there's ubiquitous computing, sensing, big data. There's rapid advances in materials, substantial cost reductions in PV and batteries. Everybody's excited about that. And an increasing commitment to climate action. That's the good news. We also have disruptive technology taking hold, rapidly changing energy system, at least for electricity. And General Clark did mention, we have to decarbonize the entire system. Changes in mobility that are affecting primarily light-duty transportation, the 271 million, that was just the US. There's over 2 billion vehicles on the road in the world using liquid hydrocarbons. There's new entrants in the electricity production. There's additive manufacturing. I think that's going to change manufacturing quite a lot. Internet of Things, artificial intelligence, unmanned aerial vehicles, a lot of things happening. The opportunity for us is to decarbonize primary energy, but then also to use carbon and hydrogen in the secondary energy and in products, including synthetic hydrocarbons and in the long-lived infrastructure. And we'll talk a little bit more. And also to mine the atmosphere to draw down that excess CO2 that was mentioned. We cannot, I think it's really important to keep in mind that we cannot forecast the future. As much as we'd like to think we can steer things, it's way too complex, way too adaptive. We cannot predict how this energy transition will unfold. That's just, I think, a given. But a couple of things we can be confident. One, we must decarbonize primary energy for all sectors. But unfortunately, we cannot turn off fossil with a switch. That would cause really bad things to happen, unfortunately. Solar will continue to grow, and eventually, because it is so scalable and because we do have to get off fossil, it will become the primary energy source. The question is when, and will it happen fast enough? Note, I talk about solar, but wind, biomass, hydro, they're all derived solar, so when I say solar, really, you can include all of it. Storage will be essential. The current system, fossil energy, is storage. The current system is based on storage. We are, with the renewables, we're eliminating the storage. And batteries, while they're coming down in cost, they're doing great. They're going to be a big part of the solution. They're not the only game in town, and they're really best only for a few hours. So we will need long-term storage and long-distance transport of storage. Also, CO2 removal from the atmosphere and from the ocean, should mention that, will be necessary. There's some equilibration, so if you take it out of one or the other, kind of equilibrates, so maybe we only need one, not sure. But because we're not moving fast enough and we haven't started early enough, we almost certainly will overshoot the 450. I hate to say that, and I wish it weren't true, but it probably will be. So, a few takeaways. I'm going to give you all my punchlines up front and then go backwards. So, it's important to say that there is a tendency out there for magical thinking. I try to be very realistic, although my colleagues say I have to tell you I err on the optimistic side of realistic, but not all the way to magical thinking. I'm pretty sure of that. I am a scientist engineer, so I lean towards what's possible, that's the science, and what's practical or plausible, or what could be, that's the engineering. I'm actually a little less optimistic about policy and governance helping us to get to the should be. But the should be is outside the realm, and we need to think about that, and we need help on that. we have proven, and Chip said this, we have proven we can engineer some very complex yet very cost-effective things. And unfortunately, sometimes there's unintended consequences. But then we can go back and usually we can fix a lot of those unintended consequences. Most people do accept there are no silver bullets. Maybe there's silver buckshot in seeking solutions, and I don't know who to credit to that to, but I've been saying it for almost 2 decades. But people, and I don't know about this room, and I know what this AREI-Day is about, hydrogen and carbon, but a lot of people believe PV, wind, and batteries is pretty much all we need, and we can do everything with that. I don't think that's true. I don't think people here believe that, but a lot of people do. And there is therefore a tendency to let the perfect be the enemy of the good and to throw the baby out with the dirty bathwater, for example, by demonizing carbon dioxide, which has a lot of very great properties, demonizing hydrocarbons. What we usually do in making progress is we preserve what's good and we fix what's bad. We don't throw it all out. So I guess that's sort of a little plug of maybe we shouldn't be so fast to say, let's put all the fossil energy companies out of business. They're evil. Hydrocarbons are evil, get rid of them. And independent of, so we're going to talk about hydrogen, but independent of how much hydrogen penetrates the energy system, that's, between batteries and hydrogen, there's a lot of debate. People will say, hydrogen is dead. I don't believe that. Predictions do still suggest about 18% of the future energy system is going to be hydrogen energy system. But we also need hydrogen for ammonia, for plastics, and many other essential materials and reactions, including steel. So I want to also give you a sense that there's a lot more we can do with hydrogen than just make electricity for our cars and for our grids, or heat, for that matter. We need hydrogen directly or to make synthetic hydrocarbons for long-term storage and for long-distance transport of energy. So I do believe it will be a significant part of the energy system. We can't make materials or chemicals out of electrons. What we forget about is as we're getting rid of hydrocarbons and we're substituting renewable energy, there's no mass, there's no materials. We still have to make a lot of stuff. We can't make it out of electrons. And batteries or transmission lines are not a viable way to export energy. For example, I work a lot in Australia, and Japan are in a lot of talk of how they get energy from Australia to Japan, and hydrogen is the answer. Oh, going the wrong way, that's why. Okay, and the current system, I said this, is based on chemical storage, but it's based on ancient sunlight and sequestered carbon. We need to worry as much about how we wean the world off of fossil and not have serious dislocations as we're doing it. That's going to be a little more challenging than I think we fully appreciate. And the preferred end state will depend on that pathway, as I said earlier. And synthetic hydrocarbons, even if you don't think they're the best answer, in a holistic sense, they may have a very important role in smoothing the transition and avoiding any dislocations. Okay, so I don't have to say a lot about this. General Clark already did. Concentration is too high. It's already over 400. That's a total of 3.1 teratons of CO2, 3,100 gigatons. That was the cumulative. General Clark showed that also. And the 2 degrees giving us the carbon budget. So for 450, that's the 2 degree. 3,500 gigatons is all we can have in the atmosphere. The excess we'd like to think of is a resource and or needs to be considered as a waste cleanup problem, one or the other. I prefer to think of it as a resource, like how much can we do with it? 1,300 gigatons of CO2, by the way, if we can make $10 per ton profit, that's a $13 trillion industry. Big opportunity. The central challenge of our time, as we said, we're going to need carbon dioxide removal. We'll probably need a price on carbon one way or the other, almost certainly, and we will have to remove the excess mobilized CO2. Now, the concentrations and the emissions, just to remind you, CO2 accounts for about 76% of the greenhouse gases. The biosphere takes up 35%. That's more good than bad, certainly, but the ocean takes up another 25%. That's leading to acidification. That's bad. 3,100, as I said, gigatons of CO2 in the atmosphere now, was 2,200. Beyond 3,500 is too much. The proven fossil reserves, this is why we say we can't keep burning it, 2,800. That's just the proven reserves, and we're still exploring. Cumulative budget, maybe 900, plus or minus. That would be 4.25% year-over-year decrease in all sectors to live within that budget. 34% in 10 years, over 56% in 20, and over 80% in 40 years. That's a year-over-year increasing percent. Restore the carbon balance is essential. Actively mine the CO2, and unfortunately, we'll probably overshoot. And I'll remind you the 13 trillion that wasn't supposed to be there again. So there's different ways of thinking about the pillars, but I wanted to put, there's no question we have to decarbonize. But as we're decarbonizing primary energy, emphasis, primary energy, we decouple energy from materials. And that means a major energy transition in a very short period of time. If we think about the material world can be a carbon sink and a role for hydrogen. We have to think about that world as well. Currently, there's large greenhouse gas emissions. Direct air capture of CO2 and hydrogen could be used as feedstocks and address the overshoot. We will have to capture and dispose, long-term sequestration. It's going to have to be safe, unfortunately, but in the spirit of we need to close the cycles and do like the biosphere, get to a circular economy, we shouldn't be looking to do that first. We should be looking to do that as our last resort. And I don't think we're talking much here about adaptation, but at 2 degrees, there will be a lot of suffering. We're already seeing suffering, and there's no two ways about it. So adaptation can be important. But on the material world, multi-gigatons CO2 per year is what we have now. 40 per CO2, it's more like 10 for carbon. Industries on that size, not many industries on that size, but they all need to be decarbonized. They are gigaton size. Steel, concrete, aluminum, agriculture, fertilizers, of course our coal, oil, and gas, and plastic are all gigaton. Plastic is approaching gigaton. It's pretty close. Not going anywhere. Oh, here we go. So energy transitions are not unprecedented. You'll hear that a lot. A lot of people say, oh, what's new? 2 previous energy transitions, traditional biomass, which was not considered sustainable, to coal, and then coal to oil and gas. We know that. But if you look at it on an absolute scale, not on a relative scale, those transitions added new sources. They didn't eliminate. The transition to renewables and fossil-free is completely unprecedented, especially in scale and time. Some people will say, okay, well, horses to cars, and landlines to mobile, but I don't think it's quite the same. So we could argue that if you want. But little sobering piece of news, electricity is where we're thinking we're making the best progress so far? Maybe not. Nuclear, renewables in 1990 were 19%. A lot of that is hydro, of course. Nuclear was nearly 17%, so carbon-free was 36%. In 2014, carbon-free is 33%. I find this sobering. I don't know about you. But since I gave you some bad news, thought I'd give you a little bit of good news, a little bit off topic, but 1 in 7 people still lacks electricity, mostly in the rural and developing regions, with the exception of sub-Saharan Africa, which is still troubling, of course. We're making good progress. We need to tackle the problem in sub-Saharan Africa. But so there's not all good news here, but it's more good news than bad news, I think. Okay, fossil fuels, I've said this, long-term storage, buried sunshine. Prehistoric biomass processed for millions of years, ancient stored solar energy, sequestered carbon. We can emulate the natural process, but do it on, rather than taking millions of years and burning it in centuries, we just have to make it as fast as we consume it. And we can do that with chemistry. So, hydrocarbons are, as I said, let's not demonize hydrocarbons. They're energy dense, they're conveniently stored and conveniently distributed. They can be transported economically over long distances. We have trillions of dollars of infrastructure and know-how. We shouldn't throw the baby out with the dirty bathwater. Lots of possible energy carriers. Now, I emphasize we do have to decarbonize primary energy, but primary energy can be turned into secondary energy and a number of energy carriers. And in the spirit of, we can't exactly predict what's going to happen, but here are a number of good candidates that we could be using as energy carriers, and the market and other things are going to determine whether any or all of them. I think hydrogen for sure will be one of them, and I think ammonia will probably be one of them, but hydrogen, carbon monoxide, methanol, ammonia, dimethyl ether, OME is a longer chain methyl ether than dimethyl ether, and synthetic natural gas. All of these could be energy vectors and energy carriers made from renewable. Electricity as the only energy carrier, as we hear a lot, it's like, let's just electrify everything. Electricity is really best used as it is produced. Not easily stored, especially not for days or seasonal shifts. And even in the sunniest regions of the world, you can have a whole week with no more than an hour or two of sunshine on average for the entire week. Run the numbers, of course, the most sunny places in the world. We can have really bad periods of time. Okay. Without exploration, I want to come back, just say a little bit about what will happen with petroleum and why we have to think about replacing the petroleum products potentially with synthetic. So petroleum products, there's a lot of things we make from a barrel of oil. Gasoline looks like it's the first thing that's going to be displaced, but that upturns a lot of what happens in the refineries, makes things a little more difficult. And if we're only making jet fuel and maybe diesel, then you could get dislocations. It's not really clear if we can keep the pipelines going, not really clear we can make this smooth transition, or at least I haven't seen someone lay it out, a nice roadmap to say it. We need to think about it. And then there's also other products. Granted, maybe 15% of the barrel. Gasoline's about 40%. We are still growing. We're growing at, I think, about 1.5% per year. This was mentioned. It's mostly driven by the U.S., by the way. Troubling. But the question is, can we shut this down without major dislocations? I think for sure if we backfill with synthetics and maybe bring it down slower and keep liquid hydrocarbons, we could make this a smooth transition and use a lot of CO2. Okay, global materials. I mentioned that there's some really big ones, but about half of the global materials, 70 to 76 gigatons per year is what we have in materials. 792 gigatons are in our infrastructure. If you want to ask how much is our built environment, it's nearly 800 gigatons. About half of what we're extracting is fossil and food, and so that goes back out as CO2. It doesn't add to the stock. And today's economy is heavily based on hydrocarbons, though, that provide both material and energy resources with the way CO2 and other processes such as being a reductant. Changes in material uses and mining demands will provide new challenges, but also new opportunities for the hydrogen and carbon economy. Carbon, I love carbon. I'm a chemist, I have to admit that. Carbon is the most versatile of all elements on the periodic table, except for hydrogen. So when you have carbon and hydrogen, there's almost nothing you can't make. And that's part of why the biological world builds everything on mostly these two and then a couple other elements, and nitrogen's the other one, which is also very abundant. But you can make all kinds of things out of carbon. You can make carbon composites. Carbon composites are better than steel and aluminum in a lot of applications. They're starting to get very much into planes and cars. BMW is building the cars with carbon composites. The only problem with carbon composites is it's more expensive. But as we get more and more, and with more 3D manufacturing, that cost is going to come down. And so we could have more of a carbon fiber, carbon composite world if we wanted. Carbon is essential for life, ensures our livable climate. We like CO2, let's not demonize it. Stored it, the bio world, the biosphere stored energy by exploiting that it can make the greatest number of compounds, more than any other element, except for hydrogen. It has superior properties, and as I say, expect cost breakthroughs as it gets deployed more and more, and it's growing quickly. Now, hydrogen, a clean, versatile energy carrier. It can be made from diverse domestic sources. Right now, almost all of it is made from natural gas. Some people are looking at making natural gas and sequestering the CO2. We could do that. There are many applications that rely on or could benefit from hydrogen. Many, not just one. So it adds diversity to the system. It can contribute to resilience, to disaster recovery. We're going to have a lot of that. It can be exported or imported. A lot of lessons learned from the LNG world. It can be used as a reductant. Now we use coal. You can pull oxygen out, for example, steel, and there are pilot plants doing it. And I can't quite see the 65, I can't see the number, kilograms of hydrogen. So I think about 65 kilograms of hydrogen per ton of steel. And you can also pull oxygen out and make more fuel for biofuels. It can be a co-product from making oxygen. Copper mining needs oxygen, and it needs energy. So you can get both at the same time. React with CO2, make synthetic hydrocarbons, I mentioned. The Hydrogen Council projections for 2050, I mentioned this, about 18%. Debatable, maybe. Energizing global hydrogen markets, 2.5 trillion annual sales is what's projected. And 30 million jobs. So, pretty big industry. Global demand for hydrogen is already growing, and that's not even with the new applications. It's primarily because of ammonia and chemicals. And 6% of global natural gas and 2% of global coal go to making hydrogen production for chemicals and ammonia. And a small amount is, byproducts, but it's mostly ammonia and mostly refining, where hydrogen is going today. Hydrogen barriers, the challenges for renewable hydrogen are really in the generation, doing it, making it renewable, getting it off of natural gas, getting the carbon footprint out of it. You can do this through advanced water splitting. There are a lot of ways of doing it through advanced water splitting that are being investigated. Electrolysis is what's being commercialized today, but I hear a lot of people say it has to be electrolysis. It doesn't have to be electrolysis. There's like a dozen ways of making hydrogen renewably, and the market and technology development will determine whether multiple, and I think it'll be multiple applications, will make hydrogen. Affordable storage, is needed, affordable distribution and infrastructure. There's already a lot of pipelines. Very quickly, because I am out of time, I see. Hydrogen integrates with both the electric grid and the natural gas grid. There's lots of natural gas distribution. We can start to transition natural gas to hydrogen, but at a minimum we can there's a lot of natural gas, even 5% hydrogen in the natural gas, which won't affect end use and won't affect the pipelines. Probably there are experiments going to much higher. That's still significant to start pulling hydrogen and not worry about the distribution. I love this chart that Toyota and the auto industry, Toyota, Hyundai, and Daimler, I think it was actually probably Toyota, on batteries versus fuel cells. Fuel cells can penetrate a lot more of the market. The low range and the, what's on the chart there? I can't see. So the weight of the vehicle, and then the average mileage. So the light duty is where we're seeing batteries, certainly, but hydrogen can go much larger. We're seeing fuel cell buses, trains, trucks, even UAVs, and fuel cell bicycle just announced. Electricity from turbines, I think you'll hear a lot more. All of the heavies, all the industry is starting to look at hydrogen for turbines. They're also looking to move from steam to supercritical CO2. This is a plant in the Netherlands where they proved it. Policy, I didn't say anything, and I'm going to skip it. Just a lot of possibilities for both producing and using. And I'm going to say thank you very much. Sorry I ran a couple minutes over.